Hello and welcome on this tutorial on Spark SQL. My name is Luca Canali. We will cover basic Spark SQL like filters, aggregates and joins. Then we will cover also a bit more complex SQL functions, and we will cover SQL array processing and Python UDF. The first thing we need to do is to create a Spark session. For this we will use Jupyter and notebooks with Python kernel, and we will run this on CERN Swan. You can also run it on your own local resources like a notebook. Back to the Spark session, this is how we create it. We are going to allocate just a small amount of resources. That's what we need for this simple demo. We'll be using Spark version 3.2.1. Some SQL just to get started. Actually, the first one is just using a Spark data frame API. We create a data frame with the numbers from 0 to 9. The column is called ID. This is the result, and there are 10 rows in this data frame. We do the same thing with Spark SQL just to show that there are two ways to do the same type of processing with Spark. The data frame is created with select ID from range 10. Range is a special function that will create these values. Another way to create a data frame for testing is the following. We create a data frame. There are 3 rows, as you can see here, and 2 columns, ID and name. And we map it to a table called My Events. To be more precise, this is a temporary view, but we will not make the distinction for the purposes of this demo. Then we select count star from the table, and we have 3 rows. Internally, Spark creates an execution plan. We can also display it with the explain command. We see that we have the table My Events, and we apply a filter. This is the logical plan, which is further refined into a physical one. We don't need to go through the distinction now. So another and similar syntax to create test tables uses the SQL function values. Again, we have ID and name. Then we want to cache this table in memory. This is not being done before an action is triggered, so we use count, which will count the rows in the table, and as a side effect we will also cause the caching to work. And then we map it to a temporary table T1, and then we want to list all the tables that are known to Spark at this point. These are the 2 tables that we have just created. We can see the details with print schema or using SQL describe. This will show the column names, the data types, and if the values are nullable or not. Okay, let's start with some very basic SQL, an increasing order of complexity. Let's just select the 2 columns that we have and create a third one, which is computed. This ID modulus 2. And then we do show, which is the action that triggers the execution of the SQL, and then it also displays the results. Let's add a filter, a condition where ID less than 3, and we have only 2 rows. And a little bit more complicated, a group by, so an aggregation where we count a number of samples and we sum the IDs, and this is the result. Let's move on to some more complex SQL for the data analysis. Let's see joins. For this first, we need to create the test tables. A table called employees, another one called departments. This is a standard table set that is used to demonstrate joins. So we have 3 rows here, 3 columns as well, ID, name, and department ID. And for departments, there is ID and name. There is a relationship between these 2 tables, a one-to-many relationship. There are no foreign keys in this system, but the data provides the relationship anyway. So let's see with the join how this relationship works. So we want to display employees ID, name, and department name. So for this we need to query from 2 tables, employees and departments. We join them together, and this is the join condition on department ID on employees table and on ID on departments table. Now we order it, and then we take the data as an action with 2 pandas. This retrieves it as a pandas data frame because there is a nice visualization of data for pandas data frames in Jupyter notebooks. And these are the results. A slight modification of this is with the left outer join. You may remember from SQL courses about outer joins. This left outer join provides all the values of the departments table in the result, even if there are no matches. So here we have department 3 that shows up. It was not there in the previous join that was called inner join, and is matched to none. Something that comes up frequently with advanced analytics are window functions. We see here an example where we want to query from employees table. We display the ID, the name, department ID, and then we want to have additional information that aggregates over multiple rows. So for example, we want to have the greatest ID of a given employee given the same department of the employee that we are displaying. Let's see the result of this query. Ignore the warnings, that's about performance, but we don't need to care because we have a very small table here. So the first employee is employee 1, and the greatest ID of all the employees in the department of where employee 1 works is the number 2. We can also query with this lag name over order by ID. The previous employee that was hired just before the current one. Nobody was hired before employee 1. Employee 1 was hired before employee 2. Okay, let's move on with something different. This is about Jupyter notebooks. We can define so-called magic functions. In particular, we define this one that is called SQL display, which allows us to run SQL without the additional Spark.SQL function call. You can just put the SQL in the notebook cell. This is how it works. We will use it also for the next example, which is the FizzBuzz example. It's a standard and well-known test. You can get the details here. So it prints all the numbers, let's say from 1 to 20. And then for all multiples of 3, we print fizz instead of the number. And we will see also the additional details. So for the ID 1, we print 1, and 2, then we print fizz, and 4, then buds, because it's a multiple of 5, and then we move on, for example, up to the number 19. And we can continue. And this is the same SQL, but this time with the standard syntax, Spark.SQL, and a string to be executed. Array processing, it's another topic, can be complex in systems that process SQL and structured data in general. But they can be also quite important, in particular for engineering and physics. Spark has some optimizations. We'll see here a couple of examples. First, we need to create some example data. This will be a schema that has an ID, which is an integer, and then the other column is temperature in Celsius that represents an array of readings of temperatures. Some basic functions allow us to get the first element of the array or the maximum value in the array, as in this. We see 35 is the first value here, and 42 is the maximum in the first row. There are some powerful functions in Spark SQL called higher order functions. They exist also in some other systems, but not all SQL systems have it. And this allows to operate functions inside the elements of the array. So this is the function that converts from Celsius to Fahrenheit, and we apply it to all the elements of the array using transform. The results of the computation is as follows. So here we had our temperature readings in Celsius, and now we have them in Fahrenheit. Similarly, we can apply higher order functions for filtering. Let's say we want to filter for temperature higher than 38 degrees. So we get the high temperature values over here, and this is the function is called filter, and this is an example of it. For reference, in standard SQL, in many systems that operate in SQL, you have functions to operate with arrays, and you have those also in Spark. They're called explode, that takes the arrays into table rows, and collect list that goes the other way around, takes a bunch of rows and puts that into a list or array if you wish. So if we run this, we get the same result as the previous example, but in terms of performance, if the table was much bigger, this would be much slower. We can also do aggregation with the aggregate function. For example, here we can compute averages. This will go through all the array values and will accumulate the values and then finally divide by the sum. So we get the average. For complex schemas, we have an example here inspired from physics. Here we have events with some details in a struct. And then we have an array of muons with some details of the muon. Okay, this is a struct. The schema is complex, as you see, it's indented. So we have a struct, and we have an array of struct. And it becomes increasingly complex to operate on nested schemas, but it's definitely possible. Let's say here we want to get some values from the struct, and then for the arrays, let's say we take the first element. Then there are similar functionalities for maps instead of arrays. This creates a data frame with maps, and this does the transformation inside the map with higher order functions. We transform values instead of transform, as we've seen before. Okay, if all the SQL functions, the standard ones, the advanced ones, and then the array ones are not enough for our processing, we can extend the functionality of Spark with user-defined functions. It's possible to write them in Scala and in Python. We'll see here some examples in Python. The first is a basic Python UDF. We define a slow function that takes an input and just returns 2 times the input. So very simple. And in between, it sleeps for 1 second to simulate doing some work. And then there is some technical point that is registering this UDF so that we can use it with SQL. Let's run it. The first time we run it we warm up, and then we run it only in 1 row, and then we run it on 10 rows. You can think of what you can expect for the timing that we are going to measure. The first time that it runs, it takes 1 second, and then when we run it on 10 rows, as you may expect, it takes 10 seconds, 1 second per row. There are some optimizations called pandas UDF. We see here an example. You need to import a few things first, and then with this decorator, pandas UDF, we define a function that multiplies the 2 inputs. In between also runs a sleeper for 1 second. And again, we need to register the function. We do a similar test as before. First we warm up, then we run it on 1 row, then on 10 rows, and then on 10,000 rows. So what we see is that 1 row takes 1 second, 10 rows takes still 1 second, and 10,000 rows still takes basically 1 second. This is because pandas UDF will send the data in batches of 10,000 rows, and data will be sent as pandas series. And the multiplications can be done on pandas series in just 1 go, so in a way that is array processing if you wish. So what happens if I run it on 10,001 rows? We are running it, you can think about it. It took 2 seconds, as you can see. That's because 2 batches were run, and each batch took 1 second. Okay, let's move on with some additional slight modifications around the pandas UDF. The first one is that you can use the type hint decorator as here, where it makes more evident that the inputs are pandas series and the output is a pandas series. And then another one that I want to show you is mapping pandas. It's a different syntax that you can use for mapping using pandas and arrow serializations. You can use it to map a function into a data frame. Okay, this ends our tutorial, so we can also stop the Spark session.